In this lab, I observed the motion of an object moving at a constant speed, an object with constant velocity. I compared my observations to a computational model of the object's motion and evaluated the differences between the predicted and observed motion of the object. The actual motion was well modeled by the computational model, but was not perfectly modeled due to various factors including human error and outside forces acting on the system. The object I observed moving, the system, is a roll of tape, shown in this video. Using Tracker software, I was able to create a table of various position versus time points, which are shown in the table and graph on the right of the screen. In Tracker, my axis is oriented so the positive x direction is toward the right, which makes the tape move in the positive x direction and have positive velocity. I then created a computational model to predict position versus time points of the tape if it was traveling at an exact, truly constant velocity. I created this model based on Newton's second law: velocity equals net force divided by mass multiplied by change in time. In the calculation section of the model, Newton's second law is used to predict the object's velocity at each time point. Then, the object's position is updated using the equation position final equals position initial plus velocity multiplied by change in time. To begin, time step, initial and final time, and initial position in the model were set identical to known values of the observed system. Then, I had to begin making assumptions about the system and the forces acting upon it. Mass was set to 1 to ensure it did not interfere with the calculation of motion, though in actuality the mass value could be set to any number and still give us an identical model for constant velocity motion. I assumed the average velocity of the system would be accurately represented by a calculation done using the first and final positions versus time points from the observed model. Using this as the initial and constant velocity of the model ensured the first and final point of the observed and predicted systems would be identical. In each step, the net forces acting on the system were assumed to be zero. In Newton's second law, setting net force to 0 will always ensure the final velocity is identical to the initial velocity. Velocity will be constant. Setting net force to 0 in our model gives the constant velocity I want to use to create my predicted points. We are unable to observe all the forces that add up to give us zero net force in the observed environment, which may include air resistance, friction between the tape and the table, and the Earth's gravity. But we are able to observe that once the tape is moving, the net force is approximately 0. When run, this program created a simulated image of the motion, the ball rolling across in a straight line, a graph of the object position versus time, and also exported all predicted position versus time points to a spreadsheet. The predicted points were then put onto a graph to compare them to the observed points. This is the graph of the position versus time for the observed system and model predictions. Model predictions are shown in blue and the observed system is shown in red. The blue line of the model predictions is perfectly linear, and while the observed system does approximately follow the model, it is clearly not perfectly linear. The observed system does not have perfectly constant velocity like the model system does. The difference between observed and predicted was likely influenced by multiple factors. Human error affected the observed values as well. Using the Tracker software, I cannot click exactly in the center of the tape roll each time. The distance traveled in a single time step may have been collected as slightly higher or lower than the actual value, depending on if I click slightly to the side of the center in the previous or current time step. Additionally, in the observed system, net force is likely not exactly 0. Factors such as friction between the tape and the table and air resistance could have created a very small net force against the tape in the negative x direction, a negative net force. This would have caused acceleration against the tape, and the velocity of the tape would have decreased as time passed. This hypothesis is supported by the position of the observed system being a greater value than the model prediction at early time points, suggesting the initial velocity of the observed tape was higher than the average used in the system. Then later, observed position values are closer to the model prediction, which suggests the observed system velocity decreased over time. If the axes had been switched in the Tracker software, with the tape traveling in the negative x direction and with negative velocity, my results would have still been the same. The computational model would have initially been given negative velocity and traveled a constant velocity in the negative x direction. My final graph would look identical to my current one, only mirrored across the time, or x, axis.